Hello everyone, myself Vijayas, studying CSE AI in third sem, section Day O in Sri Venkateshwara College of Engineering, roll number 1VE 23CA054, subject name Mathematics for Computer Science, subject code BCS 301. Understanding Bernoulli's theorem, explanation and derivation of the Bernoulli's equation. Here in this video, I am going to explain what is Bernoulli's theorem with its explanation and derivation. Introduction to Bernoulli's theorem. Bernoulli's theorem describes the relationship between the pressure, velocity, and height in fluid dynamics. This presentation will also explore the definition, derivation, and even the applications of Bernoulli's equation. Understanding this theorem is essential for analyzing fluid behavior in various engineering fields. Historical background of Bernoulli's theorem. The foundation of Bernoulli's theorem was laid by Daniel Bernoulli in the 18th century. His work in hydrodynamics established crucial principles that are still relevant today. This theorem has laid the groundwork for modern fluid mechanics, influencing various fields such as aerodynamics and hydraulics. This slide will briefly discuss Bernoulli's life and the significance of his contributions to physics and engineering. Key concepts in fluid dynamics. Before diving into the theorem, it's important to understand some key concepts in fluid dynamics. These include fluid properties, flow type, and forces acting on fluids. Knowing these concepts will help us comprehend how the Bernoulli's equation applies to the real-world scenarios. Now let us see what is Bernoulli's equation. What is Bernoulli's equation? Bernoulli's equation states that in a steady, incompressible flow of a liquid, the total mechanical energy remains constant. It combines kinetical energy, potential energy, and pressure energy. This slide will present the mathematical form of the equation and the components. Derivation of Bernoulli's equation. The derivation of Bernoulli's equation involves applying the principle of conservation of energy to a fluid element. By analyzing forces and energy transformations, we can arrive at the equation. The derivation of the Bernoulli's equation combines the effects of pressure, velocity, and elevation, leading to the equation's formulation. This slide will outline the steps involved in the derivation process. Assumptions of Bernoulli's theorem. This slide will say where to apply the Bernoulli's theorem. Apply Bernoulli's theorem. Certain assumptions must be made. The fluid is incompressible, the flow is steady, and there are no frictional losses. Understanding these assumptions is crucial for correctly applying the theorem in various scenarios. Applications of Bernoulli's theorem. Bernoulli's theorem has several practical applications including aircraft, wing design, meters, and pipeline flow analysis. There are even numerous applications in engineering, including the design of airfoils and piping system. Understanding the theorem helps engineers optimize fluid flow and efficiency. The slide will explore how the theorem is utilized in engineering and technology to solve real-world problems. Limitations of Bernoulli's theorem. While Bernoulli's theorem is powerful, it has limitations. It does not account for viscosity, turbulence, or compressibility in fluids. It assumes incompressible, non-viscous fluids and steady flow. These assumptions may not hold in real-world scenarios, which affects the accuracy. The slide will discuss these limitations and when alternate method should be used in fluid analysis. Bernoulli's theorem in real life. Examples of Bernoulli's theorem in real life include the lift on the aeroplane wing and the operation of carburetor. The real-world examples include airplane lift, car aerodynamics, and water flow in pipes. These scenarios demonstrate the theorem's practical relevance in everyday life. Understanding these applications of Bernoulli's theorem helps to visualize how the theorem influences everyday technology and natural phenomena. Experimental validation. Numerous experiments have validated Bernoulli's theorem. These experiments often involve measuring pressure and velocity in controlled environments. This highlights some key experiments and their findings that support the theorem's accuracy. Summary of the key points in this presentation. In summary, we explored the definition, derivation, assumptions, and applications of Bernoulli's theorem. Understanding this theorem is fundamental for fluid mechanics and engineering applications. Let's recap the main points discussed in this presentation. Conclusion of this presentation. Bernoulli's theorem is a cornerstone of fluid dynamics, providing insights into how fluids behave under different conditions. Mastery of this theorem is essential for engineers and physicists alike, enabling them to design and analyze systems effectively. Thank you for your attention to listen. Thank you.